The history of life on Earth spans nearly 4 billion years. It is a story of how species originated, branched out through the environment, and either endured or became extinct. To unravel the mystery of life's shifting forms, dedicated researchers are piecing together evidence from the earliest days of Earth's history. They are the time detectives.
Looking at fossils and paleontology, a lot of it is like a big detective story. And you kind of get the excitement, I think, of a detective story when you start reading it, what's going on, what are the clues that you're going to get.
One of the big ingredients of all of evolution, including the origin of life, is time. These things seem to take forever.
If we want to understand the present, and we want to understand extinctions that are going on in the present, it is useful to study extinction in the past. The past can be the key to the present.
Over vast stretches of time, evolution has shaped all living things. Yet its exact history remains among the deepest mysteries of science. From a distance, we see the Earth as a peaceful globe floating in silent space. But distance conceals the violence that rages below. Here, on the warm surface of a turbulent world, the story of life began.
At the dawn of our solar system, over 4.5 billion years ago, the Earth formed in a molten mass of gas and rock. More than 1 billion years passed before its surface became habitable by the first forms of life, bacteria. These simple cells evolved for another 2 billion years. Eventually, those using photosynthesis released enough oxygen to change the atmosphere. This paved the way for more complex cells and eventually multicellular life forms. Further in time, as organisms developed hard body parts, they left behind a trail of evidence for future scientists to follow.
Recently, workers at this reservoir construction site unearthed major clues to life that existed a mere 1.5 million years ago. Called fossils, these fragments of the past tell paleontologists, like Kathleen Springer and Eric Scott, about the lives of ancient animals and the environments in which they lived.
Fossils are one of the ways, not the only way, but one of the ways that we can learn and have a clue as to what organisms did in the geologic past, how they evolved, what they look like. As paleontologists, we're striving to reconstruct the past. The fossils that we're finding here in this valley are a snapshot in time. The animals we are finding are a suite of Ice Age mammals that lived at the very end of the Cenozoic era, right before the geologic recent. The geologic recent actually started 11 or 10,000 years ago.
You ready? Yeah. Let's go.
The large herbivores, the mammoths, the bison, the camel and the horse, which liked grass lands, give us an indication that there were very large grassy areas in the valley and outside this valley as well.
By uncovering the clues locked in these ancient bones, these time detectives can begin to explain how different species evolved.
One of the things that we do is we try to reconstruct phylogenies, and that's just a fancy word for family trees. The trunk are the ancestors, and the branches that radiate outward are the descendants. And we're always trying to figure out how an organism fits in this huge scheme of things on the phylogeny of life.
When scientists study speciation, what they're studying is how one animal evolves into a different species of animal. And thanks to the fossils we've been finding in this valley, we can now interpret that with at least one lineage. The lineage in question is this animal here. This is an extinct kind of giant ground sloth. And thanks to finding this, we've been able to relate this jaw to other jaws from nearby that are much earlier in time, by more than 1 million years, specifically this specimen here. If you look closely, you can see that these two jaws are very, very similar in shape. You have the same cheek tooth row, you have the same canine tooth there at the end, you have the same structure there. The main difference between these is obviously one of size. This is a much larger animal. And what has happened is that through those 1 million years of evolution, this tooth here has changed in shape, and eventually you have a new species, a different species that's evolved from this one.
In addition to marking the evolution of new species on Earth, fossils record changes to the Earth itself. Using these tiny fragments, scientists can trace the motion of entire continents.
If you see any clays like this, green reduced clays, that's exactly what we're looking for.
Scientists believe that all the Earth's land masses once formed a vast supercontinent we now call Pangaea. Almost 200 million years ago, violent forces under the plates of the Earth's crust broke the land apart, forming the continents we see today. As these tectonic forces moved continents, they also moved living organisms and the fossils they left behind.
Fossil evidence was the most compelling and the earliest evidence for the concept of continental drift. One example is Mesosaurus, which is in Brazil, and also it's found on the west coast of Africa. Well, you can put Africa and South America together neatly and you get the fossil range of this animal. But now they're a whole Atlantic Ocean apart. Well, was it a good swimmer? And fossil evidence was extremely important in formulating the theory of plate tectonics.
Fossil concentrations like this one are rare, but scientists have found other records of life in the ice ages. The fossil deposits of the Rancho La Brea tar pits offer Dr. Blair Van Valkenburg a wealth of clues to life in the recent past. The site is particularly rich in her favorite group, the carnivores. These fierce predators were attracted by other animals hopelessly caught in the sticky trap.
My studies revolve largely around reconstructing the lives of past carnivores that are long extinct. And there are animals which were hyena-like, and there are animals which are cat-like, saber-toothed cats. And in order to reconstruct those animals, I have to use modern analogs. So I study modern carnivores, and look at their teeth and their skeletal adaptations for locomotion. And then I use those same measurements to go into the past and measure fossil animals and then reconstruct their habits.
By studying traits such as bite pressure among modern carnivores, Dr. Van Valkenburg has deduced that saber-toothed cats made the world a much tougher place to live 10,000 years ago.
Every time an animal caught something, they probably had to worry about that big saber-toothed cat that was over its shoulder that was going to come up and steal it. And so there was a big incentive to eat everything that you got. So competition appears to have been more intense.
Fossils provide another piece of evidence crucial to any investigation into the past, a date in time.
Radiometric dating was developed in this century, and it involves taking advantage of a situation where we have isotopes, that is, elements which have different forms, that one of which tends to be less stable than the other. And it will decay from the less stable to the more stable forms.
Because these isotopes decay at a regular rate over millions of years, scientists can use them to date the rocks near the fossils they find.
It's absolutely essential that we have dates and that we can arrange fossils in some sort of order from oldest to youngest so that we can understand evolutionary transitions. Without having dates, we can't look at evolutionary rate. We can't look at the rate at which new morphologies arise.
How long it takes to change one body part into something else is a fundamental question in the riddle of evolution. Scientists are finding clues in the study of modern animals and their homologous structures.
The canine tooth of a saber-toothed cat is homologous with the canine teeth of your dog or the canine teeth of ourselves, for that matter, because all of these teeth descend or represent modifications of a similar structure in a common ancestor that would have existed at the time of the dinosaurs.
Using fossils and other evidence, scientists reveal the dynamic nature of life through time. While this evolution often proceeds gradually, it sometimes appears in sudden flashes of cataclysmic change. As scientists dig deeper into the layers of Earth's history, they leave behind the mastodons and saber-toothed cats of the Cenozoic era and enter a new world. In this earlier time, the first mammals scurried in the underbrush of warm coniferous forests, while giant reptiles dominated the planet. Punctuated by dramatic changes on a global scale, events of the Mesozoic era profoundly affected life on Earth. Paleoecologists like Dr. David Boucher study these periods of transition with keen interest, looking for clues to explain the Earth's environmental history.
We can usually see that, for example, if we have periods in Earth's history where they are warmer periods than they are nowadays, it seems as if we have an expansion from the equator outwards towards the poles of organisms that really like warm climates. So you can imagine that if nowadays we were to become a much warmer globe, perhaps organisms that are more typical of the equator, of the tropics, would move northward. We can actually track this in the fossil record and see organisms adapting to these warmer temperatures by moving north and south to what were once colder areas of the Earth.
As the Earth changes, its organisms must also change and adapt in order to survive.
Life itself has certainly, through the process of evolution, tried to adapt to the changes that we see on Earth. And many of these changes are slow. And evolution itself is typically a very slow process so that it can keep pace with geological changes, changes in environments, changes in mountain building or whatever. So life evolves and changes in that manner. If we look in the fossil record and try and understand how evolution operates, we find two things going on that are the components of evolution. One is speciation. We see new species forming or evolving. And the other is extinction. Extinction is always happening. It's not something that we can ever get away from. Species become extinct.
Fossils have revealed the birth of new species and the passing of old ones, but these events appear unevenly through time.
It seems as if the evolutionary process actually may operate more in sort of fits and starts rather than as a smooth unraveling of evolutionary processes, this idea of punctuated equilibrium where species actually appear rather rapidly.
This idea explains the so-called gaps scientists have found in the fossil record. These may not be gaps at all, but periods of dramatic change in Earth's history.
Sometimes we have changes in the Earth's environment that are on a much more rapid scale than that which evolution progresses at. And then we get things called mass extinctions. Mass extinctions are where the rate of extinction dramatically increases over what we normally call background extinction, what should normally be going on. After mass extinctions, the survivors are able to undergo rapid evolutionary changes as they take advantage of the empty ecospace. It's a pretty sweet time for the survivors.
It's hard to imagine even one event so catastrophic that it can decimate whole populations. Yet the record shows this happened several times on a global scale. The most devastating event marked the beginning of the Mesozoic era.
The greatest extinction that has happened on Earth, which is at the end of the Paleozoic, where somewhere around perhaps 90% of species in the oceans died out. At the same time, a giant outpouring of lava and flood basalts in Siberia. Today they are preserved and they're known as the Siberian traps. But apparently this huge volume of lava came out in the space of 1 million years or so, and the volume is such that if it were to have covered the whole surface of the Earth, we would cover it 15 feet deep.
Just as the Mesozoic era began in catastrophe, scientists believe it ended the same way, this time in a single explosive event.
Perhaps the most spectacular kind of event that can cause catastrophic change on this planet is a collision with an extraterrestrial object. We now have extremely good information that a giant asteroid hit the Earth, perhaps in the vicinity of the Yucatan Peninsula, and left a layer of extraterrestrial material in the rock record for that time interval that is found around the Earth. And it's thought that this really was what put the knockout punch to the dinosaurs. With the mass extinction, dinosaurs are gone, and the mammals undergo a huge rate of evolution for about 10 million years afterwards and evolve all the different kinds of mammals that we know about, bats and whales and all sorts of things that did not exist beforehand. So it provides a real opportunity for the survivors to make hay.
With extinctions come new opportunities for the rise of other organisms. Dr. Botcher hopes to explain the mechanisms that drive these pivotal events in the evolution of life.
Organisms perhaps have been killed off by different ways other than just asteroids or volcanic eruptions or whatever. So we need to really do a comparative study of mass extinctions, their ecological effects, if we're going to try and understand perhaps what the effect of the mass extinction that we might be the cause of will be in the future.
Throughout Earth's history, the only constant we find is change. It has shaped the evolution of all living things. Ours is a restless planet, and it has been so since life began. As biologists travel further back in time, eventually they must face the most challenging mystery of all, the origin of life. How did it come to exist? To answer this question, scientists must probe back over billions of years, before fossils recorded time.
Fossils from the Cenozoic and Mesozoic eras, in fact all records of multicellular organisms, occupy only 1/5 of Earth's history. Eukaryotic cells appeared long before, preceded by the first bacteria, which formed over 3.8 billion years ago. In the vast span of Earth's history, simple cells ruled the world, yet their origin is still a mystery.
Scientists wonder about the time before the first cell, when there was no life, only chemicals.
We have to think about not only the Earth as it is today, but also as it was when life got started, that seemed to be well adapted for starting a living system. The important factors are that the temperature be right, so that the water not be frozen in ice, so that it not be boiled into steam, that it be shielded from dangerous radiation.
The atmosphere, too, would have to offer the right combination of chemicals. In the mid-20th century, chemist Harold Urey was one of the first to recognize this, proposing an early atmosphere of methane, ammonia, water, and hydrogen.
Urey had a student, Stanley Miller, a graduate student, who performed what has to be regarded as one of the most sensational experiments of the 20th century.
Well, I think that nobody had really approached the problem of making the origin of life, at least on an experimental basis. And it seemed obvious to me at the time that the methane ammonia atmosphere would be likely to make organic compounds. But you never know about these things till you do the experiment.
Miller placed the gases and water in a closed system, then boiled the mixture with a spark running through the vapor to simulate lightning. He watched and waited, wondering if these simple compounds would produce the organic molecules necessary for life.
The experiment worked very easily once we got the apparatus built. And the first couple times we didn't have it quite right, but the third time the organic material just poured out. You could just see the yellow and red material being formed on the electric discharge. We got these large yields of amino acids. We had hoped that maybe we might get a trace, but we got several percent amino acids produced in the spark. The synthesis of amino acids and other organic compounds, of course, is not the same as synthesizing a living organism. How you get a molecule to reproduce without the use of enzymes and complicated apparatus that we have in living organisms has not been worked out.
Scientists believe one factor that led to the origin of life was the relative absence of oxygen in the Earth's primeval atmosphere.
Oxygen is one of those good guy, bad guy chemicals. We all know we need oxygen to breathe today. But oxygen is a dangerous material. It gets in there and destroys many organic molecules. Until various mechanisms of defense evolved, you had to keep your oxygen, free oxygen, at arm's length.
The lack of free oxygen permitted molecules to organize into the first cells. Many scientists believe these simple bacteria lived on without much change for almost half of Earth's history. Then, growing levels of oxygen from photosynthetic cells led to an explosion of more complex life forms. Biologists like Russell Doolittle are revealing these evolutionary relationships using what they call a molecular clock.
A molecular clock is a term that was invented about 30 years ago, and it had to do with the fact that you could compare protein sequences. It was known that different organisms had their proteins put together in different ways, and the more different the organisms, the more different the sequences. So that simply by looking at the sequences, one should be able to look backwards in time and gauge when those organisms last had a common ancestor. In our most recent study, we compared a large number of enzymes. Altogether, there were 531 different sequences that were involved in this study. We look through and we can see the bacteria where there are...
By comparing the same proteins in different species, biologists reveal major branches in the tree of evolution, tracing the development of life from the first cells to Earth's most complex organisms.
Amazingly, bacteria and us share a large number of critical macromolecules. Most of our enzymes have equivalents in bacteria, and it's those that are the ones that are the most useful for making these long-scale clocks, for example. Our measurements point to a divergence time about 2 billion years ago. Right, let's hit that. Look at it and let it search. Take an enzyme made of, say, 250 amino acids. There are 20 amino acids that are well known in the world, in all organisms, and when we look and see what the order of those 20 amino acids are, we find that 40% of them are exactly at the same place. There's no possible way that that could have come about by chance. Furthermore, when we look at all the organisms in between bacteria and us, the numbers will creep up towards us. By the time we look at, say, yeast, now 60% of the amino acids may be in exactly the same place. By the time we look at some other animal, we're up to 80%. By the time we look up at chimpanzee, it's 99%. So the evidence seems irrefutable.
I'm pleased with how that
In tiny molecules and massive bones, scientists uncover the clues that will solve the mystery of evolution. These time detectives have gathered a massive body of evidence that supports this account of life's history. But, as with all scientific theories, important questions remain unanswered.
The most difficult question is probably the origin of life, where we don't have nearly the detail that we have for the subsequent evolution. But the other uncertainties in evolution really just matters of detail and rate, and whether it happens suddenly or gradually. But the fact that evolution took place is, I think, beyond question.